Hey, hello there, and welcome back to another Advent of Code episode. So today we are going to continue where we left off last time. Oh, look at this Advent calendar. Yeah, so the last thing that we did was day 13 in these mountains on the lava island. And look at this, 14 is on the top, and we also need to do day 15. But let's give first day 14 a try. Although, well, if I'm just going to take a look, and if it looks like a very difficult puzzle, I might skip it and try the day 15 so I can get back up to date and leave this for later. But let's see. Parabolic reflector dish. You reach the place where all the mirrors were pointing. A massive parabolic reflector dish attached to the side of another large mountain. So this is like like a parabola, like the Arecibo Observatory. Okay, the dish is made up of many small mirrors, but while the mirrors themselves are roughly in the shape of a parabolic reflector dish, each individual mirror seems to be pointing in slightly the wrong direction. If the dish is meant to focus light, all it's doing right now is sending it in a vague direction. This system must be what provides energy for the lava. If you focus the reflector dish, maybe you can go where it's pointing and use the light to fix the lava production. Okay, cool. So this is using like it's another grid puzzle. We're having a lot of grid puzzles in this Advent of Code. And so far, we haven't have any grid puzzle that's involved like finding a shortest path, like a pathfinding algorithm, which I'm surprised about. Maybe it will be this one. We shall see. Okay, and so we are using a giant dish of mirrors to use it like to focus light on a point and I guess melt rock and produce lava. That makes a lot of sense. Upon closer inspection, the individual mirrors each appear to be connected via an elaborate system of ropes and pulleys to a large metal platform below the dish. The platform is covered in large rocks of various shapes. Depending on their position, the weight of the rocks deform the platform, and the shape of the platform controls which ropes move and ultimately the focus of the dish. Okay, this is a very complex system and sort of a crude implementation with putting rocks of different weights to focus a giant mirror, but somehow makes sense. In short, if you move the rocks, you can focus the dish. The platform even has a control panel on the side that lets you tilt it in one of the four directions. The rounded rocks, O, will roll when the platform is tilted, while the cube-shaped rocks, hashes, will stay in place. So lately, all these puzzles have been using hashes and dots for everything, basically. You note the positions of all the empty spaces, dots, and rocks, your puzzle input. For example, this. Okay, so there are rounded rocks that can roll when you tilt the platform, and cube-shaped rocks which stay in place. Okay. Start by tilting the lever so all the rocks will slide north as far as they will go. So here all the rounded rocks got pushed to the north, and the cubed ones are like barriers for these things. Okay. You notice that the support beams along the north side of the platform are damaged. To ensure the platform doesn't collapse, you should calculate the total load of the north support beams. The amount of load caused by a single rounded rock is equal to the number of rocks from the number of rows from the rock to the south edge of the platform, including the row the rock is on. Cube-shaped rocks don't contribute to load. Oh, that's weird, but okay. So the amount of load caused by each rock in each row is as follows. So okay, things that are further away from the north contribute less, and things that are near the north contribute more. That makes sense. The total load is the sum of the load caused by all the rounded rocks. In this example, the total load is 136. Tilt the platform so the rounded rocks all roll north. Afterward, what is the total load of the north support beams? And the input is just the giant grid of rocks. Okay. This seems like part 2 is probably going to need us like tilting this platform in all the 4 directions, like a more general solution, I would expect. But let's try to do part 1 as simply as possible, and then we should see. So let's open the code, jump to this, and open the code editor as usual. Oh, I have been taking notes of the previous solutions, copious amount of notes for day 12, which was painful. Oh, I forgot to put a space here. Let's add it. Let's amend this. Okay. And let's also close everything and copy the template as we usually do. This is day 14. Giant something dish, parabolic reflector dish. Okay. Parabolic reflector dish. Let's copy the inputs. Day 14. My input will be this. The sample will be this. Oops. And the expected output is 136. Okay. So let's get to it. As usual, I'm considering whether I should model these things as an enum of like empty rounded rock or cube rock, or just use characters as we have been doing lately. And I think I will do that. This is actually similar to day 13, where we also had a thing, and I'm just going to shamelessly copy this, and this will just be a usual grid, a vector of vectors, and I'm going to just use characters here. So we're gonna get the input lines and map each line to its characters, and then collect all of that into two-dimensional grid as usual. Okay, and then we need to tilt this thing north, move all the rounded rocks there, and then calculate their load or something like that. So how do we do that? Oh, this is not the input. This is actually the thing already tilted. This is the input. Oh, okay. So I guess at some point we are going to need, to tilt this in the 4 directions. There's definitely there's different ways that we could do this. Let me think. Like, one way is to go starting at the top and going through the bottom, And when you find a single rounded rock, push it to the top as far as you can go. And then go for the next one, and so on. That is sort of like insertion sort, in a way. And yeah, this is almost like sorting. But you cannot pass. So for example, this O here cannot pass this thing. This one here cannot pass this, and so on. So it's not just sorting. But yeah, you can go from the top to the bottom and find the first rock and push it all the way up, all the way that it can go, and so on. That is one idea. That's one possibility. Another one would be to do lots of passes from the top to the bottom, and on each pass, see if you can move each rock once, swap it once to the top. And when you can, you do it, and when you can't, you just leave it in place. And if you do n amount of passes of that, you're going to have pushed everything to the top, which is kind of like bubble sort. So this is basically what do I prefer, bubble sort or insertion sort? It's kind of the same for me. Let's go with sort of insertion sort. So we're going to have this thing mutable and call a method like tilt north for this grid. We're gonna pass it as a mutable reference, just mutate the thing in place, and then I want to count the load of this thing. But let's first implement this. So here we're gonna receive, as usual, let's extract this into a type alias grid. Oops, sorry, as usual. And now this receives a mutable grid and returns nothing. So we're going to iterate each column. So let's say for column from 0 up to the grid, or up to the width, and the width is going to be the length of a single row. And for each column, we want to find the first, well, we're going to, iterate then through all the height. So let's also have a height thing here. So for y from 0, let me think. Yeah, I wonder if I can use slicing and iterators on those slices. Actually, let me think for a little bit. Have these columns. What if we do I'm changing my mind about the bubble sort kind of algorithm, because might be simpler. So how would we do this? We would say, okay, from this up to the up to the height. I don't know if I want to reverse this, but maybe I will. And then let's call this, I don't know, I. And then we're going to go from, yeah, sort of j from 0 up to height minus I. This is kind of like remembering how to do bubble sort. And then the j is what I want. We can start at 1, I guess. So that the indices, like j minus 1 is also a valid index. So we can say something if the grid at j j minus 1 is empty, we can move the thing here, right? Something like that. So if this is empty, well, and this column, then grid j minus 1. Actually, I want to ask if the grid at, first of all, at j is a rounded, yeah, this is the character, so if this is this, then we'll swap, I think. Iterating by columns is a bit tricky, but yeah, this seems fine. Then we're going to swap these two things, right? No, not swap these two things. Well, yes, it's kind of a swap, but well, we know the symbols, so we can say, hey, this will become now an O, and the J1 will become a dot. Okay? And we do this I amount of times. Yeah, and maybe this is enough. I'm not sure. Maybe we can print this and see. So let's print these things. So for row in a grid, we're going to make string from an iterator, which is just a row, and just print line this thing. No need for anything else. Just print this, yeah, and let's run it. Cargo run, bin day 14 with the sample input. And look at that. It seems to have worked. We have pushed all the O's to the top. Nice. That was easy. Triple nested loop. Sure. Now what we want to do is to count the load. So how do we call this thing? What is the total load on the north support beams? So let's north beams load. It's gonna be some type, I don't know what. It's gonna be, we're gonna iterate over every grid, I guess, over every road, sorry. We're going to map it to like the load of that row, and for that we are going to need the row number. So let's enumerate this or zip it. Let's just use enumerate. So here we're going to receive say the y coordinates and the row itself. Okay, does this make sense? Yeah, right. We're gonna go let's like the y has to gonna need to flip it around, but okay, we're gonna map to something and then sum all of this. Okay, then how do we calculate the weight or the load of each row? Well, we're going to just iterate over each row, find the rounded rocks. So we're gonna filter the rounded rocks. Let's say filter tile, and if the tile, we're gonna filter the ones that are O's basically. And to be honest, just count these. That's what we want. Count them and multiply this with like the number that corresponds to that row. So it's gonna be, actually should be like the height minus I guess, which we can probably express in a simpler way by zipping with 1 up to the height, which the height is grid length. So 1 up to and including the height, right? And we get all of this and reverse this thing. And and then we're gonna have the row and the row load. Something like this. Does that make sense? The style is double reference, so there's double dereference that. And sure, this thing, since we are just counting here, let's make this thing AU size and let's print this. So north beams load. Okay, let's run this. Look at that, 136. Awesome. Run it with the actual input. Is this number what we want? And didn't I make any off by 1 errors? It is the number that we want. Awesome. So that was pretty straightforward. And look at these nice uses of zip. Cool. Yeah, this looks fine, at least for part 1. Let's see what part 2 is about. Part 2. Oh, and I forgot to actually put a stopwatch for this video. It must be already like 20 minutes or half an hour of this, but yeah, let's put a stopwatch. Part 2. The parabolic reflector dish deforms, but not in a way that focuses the beam. To do that, you need to move the rocks to the edges of the platform. Fortunately, a button on the side of the control panel labeled spin cycle attempts to do just that, spin cycle. Each cycle tilts the platform 4 times so that the rounded rocks all roll north, then west, then south, then east. After each tilt, the rounded rocks roll as far as they can before the platform tilts in the next direction. After one cycle, the platform will have finished rolling the rounded rocks in those 4 directions in that order. Here's what happens in the example above after each of the first few cycles. So after one cycle, okay, so it has gone north, west, south, east, then 2 cycles, this is what happens. So some little things move. After 3 cycles, okay. Is this stable? This process should work if you leave it running long enough. But you're still worried about the north support beams. To make sure they'll survive for a while, you need to calculate the total load of the north support beams after 1 billion cycles. In the above example, after 1 billion cycles, the total load of the north support beams is 64. Run the spin cycle a billion times for a billion cycles. Afterwards, what is the total load of the north support beams? Okay. Okay, can we brute force this? It's actually not like, I think it wouldn't be so impossible to brute force this. That's probably not a great idea. So I guess what I'm wondering is, does this process converge at some point? Like if we keep running this cycle, does it happen that at some point the result of cycling the platform is the same as before cycling? It's like, does this converge? And if it does, then we don't need to run this amount of cycles. We can just do it until the point that it stabilizes, and then we know that it's the answer. Yeah, but we don't know if that happens. So I wonder if that will happen. And if that doesn't happen, which is what I suppose will be the case, like if it doesn't converge, then what should happen is that it's at some point it cycles, like it's a cyclic process, and at some point you get an output that you have previously gotten. So then you can skip ahead once you have detected like a previously known output. Yeah, and you count the difference, like how many steps did it take you to get from the previously known output to the output now, like and they are the same. And so if you know that, you can skip ahead a multiple of that times till you get to close to 1 billion, and then do the so So we need to implement the cycling logic. This is tilt north. Beautiful. We could implement like tilt in any direction. Like a generic tilt function, or we can just copy paste like crazy, which I am sort of tempted to do. Okay, so let's first of all let's add let's add this solution as a part 1. So we have this sample out. If we can also add the answers that we got. So let's do a check all. For day 14, this is the answer. So here we have this, and now if we check all, this should pass. Great. This code is fine for a first version. These IJs are not very pretty names, but it's okay for me. This works. Yeah, and we are sort of swapping this. Yeah, let's commit this as a solution for part 1. So add day 14, part 1 solution. Okay, great. So this is tilting north. I am tempted to either repeat this thing 4 times and call it like tilt east or tilt west, south, and east, or just do one big function called like cycle. Let's see, spin cycle, I think it's called. Yeah, spin cycle. Spin cycle. That takes this and tilts the thing north, northwest, south, and east. So let's see how horrible this will be. What we are doing here is kind of a swap. So let's at least have a little function. Let swap be just a closure that will get the x and y coordinates and do something like grid grid y. My cat wants to play. How do we swap this? We can start at temporary or something like that, but let's write it down. We're going to assign grid y1 and x1, and I think we can do something like this. Grid y2 and x2, and then we are going to assign the swapped things. Surely is, like, I know vectors have a swap function that we can use, but I want to make this kind of generic to just receive 2 coordinates and use this in the bubble sort like things in here. But this, you don't like this. Sure, you want types for this. Let's see if once we use it, swap. So, sort of want, like, instead of swap, I would like to put this logic of, hey, try to roll a rock from this position to this other position. So instead of this, let's sort of try to do this. So forget about this. Let's try again. And let's call this thing try roll. And we're gonna receive X and Y. So if there is a rolling rock on Y1 and X1, and the Y2 and X2 is empty, then we'll put the rock on the second coordinates, and the first coordinates will be empty. Okay, and then this should become try move. Well, let's not lose our coordinates. So X will be column always. The position that we want to move from is J, and then call and J minus 1. This is sort of what we want. Okay, and this, because it's not try move, it's try roll, of course. And now cannot mutate immutable variable. Mutate? What? This is weird. No, cargo build, let's say. Cannot infer type. Okay. Okay, let's put types in here. Seems unnecessary, but if we do this, this thing needs to be mutable because it's mutating. Interesting. Because it's mutating the grid. Okay. Okay. And actually, what we have just implemented is the same as tilt north. So let's replace the code in tilt north to see if this approach, like generic approach, does what we want. Yes, it still gets the same answer, so seems to be correct. Fine. So now this thing is tilting north. Let's do the same to tilt east. Yeah. Tilt. And actually, let's use better names here. So this is gonna be X. This is gonna be, we can say I for this, but then this I want to say, okay, this is the I coordinate, so try roll, we are passing like X and Y's things. Makes sense to my head. And then to tilt east, we are going to go for every row now. So from width to height. And then we're gonna go from I to width. And then from X to from 1 up to the width again, minus I. Then we're going to try to roll from XY into X minus 1 because we're going east, that is to the left. Okay, beautiful, beautiful. Now we want to tilt south. So this actually should look like north, but the other way around. So how do we do the other way around? Well, we can sort of do the same here, but reverse the order. Like, let's not think, never think, just do what comes naturally. So we are going this is tilting south. No, wait, X is just the column, so it's not this what we want to reverse. X doesn't matter here. What we want to reverse is the order in which we iterate the Y's. So we want to go from height minus 1 up to the top, so it will be 0 plus I think. Yeah, I think, I'm not sure. We're gonna reverse this. So starting at height minus 1, it's actually going to be height minus 2 because this is not inclusive. Sure. And then we're going to try to move from xy to xy plus 1, so it is to the south. I don't know if this is correct, but let's assume it is. And let's do something similar for tilting west. Wait, is this the correct? No, oh wait, this was to the left, but I was confusing. This is west. West is the left, right is the east. Okay, so we do similarly, we go for each row for sure. That doesn't need to be reversed. What's your problem here? Consider reducing this to I. Oh yeah, okay, sure. Thank you. So here we're going to do something similar. We're going to go from I to width minus 1. But yeah, going from the rightmost to I, right? Yeah. I starts at 0, so I don't think that doing, yeah, maybe this is I plus 1. Yeah, and this is probably I plus 1 here too. But let's run one cycle, one spin cycle, and see what happens. And actually, these things, we are mutating the things, so we have already. Let's see, particular. Here's what happens in the example after each of the first few cycles. So I wonder if the first cycle starts from the initial position or from this, like the thing that we have already tilted. So let's let's just start again. It's not very pretty, but I just want to see if our tilt spin cycle function does what we want. So let's grab parse another grid, and let's do a spin cycle. Yeah, passing the mutable grid, sure, and print it after one spin cycle, like what happens. Okay, so cargo run with sample input. Yes, we did get a subtract with overflow. I was not expecting that, but yeah, okay. This is when we are moving to the east, so moving things to the right. Oh, I should. Wait, I'm getting confused now. Did I add the +1 here? When we're moving east, this should be +1. Yeah, and we start from. Okay. But this is underflowing. Why is this underflowing and not tilting north? So, oh wait. Wait. What happened there? This wasn't this underflowing? I didn't change that. Oh no, it was the thing that I changed. Okay. Okay, so it didn't explode, and this is what we get after one spin cycle. Is this what we get here? Let's actually do this and compare. So does this look like this? Yeah, right? Yeah, look at that. So we did one spin cycle successfully. Then we have 2, and then we'll have 3. That's awesome. That's great. So we need to now remember the things. Let's actually do 3 spin cycles and run this again and see again if this actually matches. Yeah, it matches this, right? Great. So our spin cycle seems to be doing what we want. That's great. Let's close the console. But now the problem is doing a billion of this is going to take some time, right? I think so. So let's see if this thing converges actually. So we have this. What if we did 100? Just do 100 spin cycles, why not? And run this now. Is this the same as before? Look at that, it looks the same to me. Hey, it looks the same to me. No, it's not the same. This O is not here. Where did that thing go? Where did it go? Can we see this? It looks very, very similar but this is not here. Oh, there's another O in here. So this is after 100. Let's just simply go up to 10 and print every time. Yeah, let's do that. Probably moving things here which we don't, so let's iterate without destructing the thing and run this now. So, okay, let's add some spacing too. Print line. Is there some like back and forth? Let's see. This is after the first one. After the second one, still not converging. This is after this. Okay, haven't this converged at this point? No, at some point this goes away. Where does it go though? Oh, now it's here. Okay, let's do something more. We are gonna do this, and we are gonna say very inefficiently, let grid copy be grid clone, and we're gonna pass the grid and just say if grid is equal to grid copy, converge. I don't expect this to happen, but yeah, let's do it 100 times. I don't think that. Okay, we are not converging. That is fine. However, let's do something else. Sorry, I got my doorbell ringing. I'll be back in a second. Pause. No, not like that. Pause. And I'm back. So, where were we? So we discovered that the thing doesn't seem to be converging. If I don't print this and don't print this and I run this, yeah, no, converged is never printed. So we're never getting the same result after a spin, like the same result as before. We are doing this 100 times. If we do this with the input, I expect this to not happen either. Why is this taking so long? That took a very long time. I'm surprised. If we run in release mode, well, it's faster, but okay, I guess our tilting and rolling algorithm is not very efficient, which I'm not surprised at, because we are using, as I said, something similar to Bubblesort, which is pretty terrible. And we are doing that 4 times, like for each direction. Yeah, it's not great. Can surely be improved, but let's not worry about that. What I want to know is how many different outputs do we see. So let's have another thing here. Let's say let's mute output grids. Yeah, or spins grids. It's gonna be a hash set. Let it infer its thing. So let's just have a set, and we're gonna store our grids in there, like the results. So spins. Is this not a? Oh, it's not with double n. Like what? Why would it be with double n? Spins grids. Let's insert. Oh, you want to import this surely, right? Yeah, import this thing, and we are gonna insert the grid, but not the grid itself, right? Because otherwise, yeah, it's going to be double borrowed, and we cannot take a mutable reference, of course. So then let's clone it and insert a copy of the grid. So now, yeah, it's a hash set of grids. And what I want to print here, let's say after I cycles, we saw grids, and is the spins grids length. So how many different things, because this is a set, how many different grids have we seen after 100 cycles? So let's run this with the sample input first to see if this makes some sense. 9 grids, okay. So after some point we stop seeing new grids, and this is pretty soon. After 9 cycles we see 9 different grids. That's surprising. I thought that there were repetitions already, but then after 10 cycles we have seen all the different grids that there are. So if we run this thing with the actual input, well, it hasn't converged yet. No problem. Let's bump this up to 1,000 and see what happens. Look at that. We saw a repetition, and now it doesn't increase anymore. So that's awesome. 119 different grids is what we saw. Okay. So now we can implement this, I think. We can implement part 2. How are we going to do this, though? Well, what I think we'll have to do, let's think. We know that these things cycle then after 119 different grids. We see, we find the cycle. So how do we do this? Thinking. Have this grid. Have this first tilt. Yeah. Okay. I'm just thinking of how are we going to do this. Okay, let's sketch it out. So this is part 2. We have a new grid to work here, so we don't need to worry about part 1, I guess. Yeah, we can leave this for part 1. We have a new grid for part 2. We have spinned grids. So let's write this thing as, I think I'm going to want like a loopy loop, good old loop, or a while loop maybe, but not a for loop, because I want to like skip ahead when I find a cycle. Yeah, that is what I want, yes. So let's see. We're gonna have a mutable cycle count, let's say, after spin cycle. Yeah, okay. I'm gonna start at 0, and we're gonna do while cycle count is less than 1 billion. We're gonna do something. We're gonna spin cycle the grid. Okay, sure. And the spin grids, spin cycle the grid. At some point we are gonna cycle count, increase it by 1. And we want to insert a copy of this. No, we don't want to do that unconditionally. We want to check if we have already seen it. That's the idea. And I realized that having like a hash set of this huge thing, like the input, like it's a vector of vectors, like a 2D grid, is a bit wasteful for sure. The actual input for day 14 is 100 by 100. Sure. We could totally optimize this. So we hash less things, but let's not think about optimization. Let's think about getting the right answer. So, how do we detect a cycle? Well, we will detect a cycle by asking if it is already in the spinned grids. Okay, so let's actually detect the cycle and break. One thing that I don't know if this is like the cycle will be exactly 119, like the number that we saw. This is the number of grids that different grids that we see. We're never going to see a one grid different than that when we spin, because we're going back to there, and so it's cycling. But I don't know if we are coming back to the original grid after a while. So we could test that, I guess. But let's first say is if spinned grids contains our grid, which I'm sure we need to pass a reference. Let's print found cycle after cycle count. So same idea as before. We're gonna break out of this loop. Yeah, and otherwise we insert it into we increase the cycle count. And finally, after all of this, we're going to do the same thing of like counting north beams load. This will be part 1. And then we are going to do the same but for part 2. So north beams load part 2, and we're gonna print that thing. Whoops, part 2. This is not correct yet. Like, no, this is not correct. We want to finish all the cycles actually, but I want to see if we still have this detection. Yeah, okay, found cycle after 119. Sure. This won't be the correct answer, but let's submit it just in case I get surprised. No, okay, it's too high. Sure. I didn't expect that to be the correct answer. So, okay, we know that we have seen this grid already. Now what we want to do is like skip ahead. But what I want to know is when we saw this grid, like on what cycle that was. So instead of having a hash set, I'm going to have a hash map. And then instead of saying contains, let's say, well, let's get this. If it is some previous cycle, we're going to spin grids get. So now the hash map will be from a given grid, and we're going to put the cycle count. Okay. Previous cycle found the cycle after. We know that this number is 119. Previous cycle. Yeah. Cycle. Okay, we are now remembering when we saw these things. So let's run this. Oh, the previous cycle was 112. It's not 0. So that means the grid that we see on cycle 119 is the same grid that we see on cycle 112. And after that, it gets repeating, like it keeps repeating. So this is now the skip ahead part. This is going to be sort of on the else condition of this. I know that this is implied by this break, but we are no longer gonna break, I think. Otherwise, yes, we insert this. Okay. Now what I want to do is skip ahead near the 1 billion mark, and for that, how are we going to do this? This is a modular arithmetic thing. So the cycle size, we can calculate the cycle size, right? Well, it is 19 minus 119 minus 112, so this is just 7. Let's say cycle size is cycle size is cycle count minus previous cycle. Okay, so we are going to add a multiple of 7 to the current cycle that we have, 119. Yeah, a multiple of 7 that gets us to just below a billion, sorry. So how do we do that? So if we do a billion mod 7, is that what we want? No, that's not what we want, of course. We want to probably divide a billion by do an integer division by 7 and then multiply by this. That's not exactly. Yes, I think what I want to do is have I think if we do it the other way around is gonna be easier, but let's do it once. Cycle size. So let's skip cycles. We're gonna want to skip the cycles of this minus the cycle count is kind of like actually current cycle, but okay, let's use that minus cycle count. So this is going to be a billion minus 112. Then all of these, I think, I want to divide by cycle size. So this is like integer division. But then we're going to multiply again by cycle size, right? Something like that. Let's print this. We know all of this. Let's say skipped cycles. Well, we're going to be skipping this amount of cycles, which it's a number. I'm not sure if I did the calculation correctly, but let's do what we say we're going to do. Instead of breaking, we are going to skip this cycle. So we're going to do cycle count plus equals skipped cycles, and then well, then the problem is that we are, well, let's actually print that. Now add cycle count, and we keep going. I don't know what will happen. Let's see. Oof, skipping 0. Okay, problem. So once we have skipped once, we don't want to do cycle detection again, so let's have a bool for that. Skipped. Blech. Horrible Boolean name, but let's have this. So if and we cannot do this, right? And not skip run, because yeah, let chains are not not a thing already. So we want to do this cycle detection thing if and only if we haven't skipped. So let's say if not skip done, we're gonna do this thing. Sure, we mark skip done, and we are going to continue with the loop. Well, the continue is not really necessary. Yes, it is necessary, because here I don't want to do else. I just want to do this. Sure. Actually, this sort of goes inside of here. Okay, I think this kind of makes some sense to me, at least. Let's run this. Well, now add, and it is just about to get to the cycle count. I probably have done some off by one error, but I don't know. 9663 was what I submitted before, and now I'm submitted this, but didn't it say that it was too high? Yeah, it is too high. Okay, so we need to have something less than 9663. So I made a mistake, but I don't know where. When we skip ahead, we're adding a multiple of this cycle size. That is okay in my head, and we are adding it. Do I need to increase the cycle count again? Because we skip a multiple of that, because we know that after a multiple of this is going to be the same again and again and again. But I think we need to still add the cycle count here. So let's not continue. Let's not skip that little +1 and see what answer do we get. Okay, 9661. This is less than before, so there is a chance that this is the right answer. Submit. What's happening? Oh, my computer is like, oof. The browser is completely lacking. What's happening here? Okay, so Firefox got screwed for some reason, so yeah, quit it. Okay, let's open it again. I have another window for Firefox. Let's put it on the other workspace. We're still here. We wanted to submit this. Is this? Yeah, okay. After the browser died, we got the correct solution. And it's a bit messy, but it works. And is that all that matter? I don't know. Let's clean some things up. So, is this nice? I don't think it is really, but we are doing the correct cycle detection. That is fine. This is the correct answer for part 2. So let's copy it. Let's put it in the answers file. The sample output that we want also. Oh, let's see the advent calendar. Yeah, nice. We have more of the lava island. Let's also record after this many cycles, this is 64 for the sample. Let's copy this and put it here. Is that correct for our sample? Yes, it is. Okay, great. So now check all should work. Yeah, cool. So let's review the code just a little bit, and then I want to cut this and hit the climbing gym, because today there is a festival there. So this spin cycle thing is, I think, fine. It's not the best algorithm by any means. I'm sure this could be much more efficient. And I'm sure that these 4 different nested for loops could be like compressed into, like, could be generalized by generalizing like a direction concept, but not really interested, I think, in that. Tilt north is like a hard-coded version of one of these, which is useful for part 1. Great. So for part 1, yeah, we're doing this, and we have a grid. So tilt north does this. Let's extract at least this little function that takes the grid and returns the north beams load, because we are doing exactly the same for part 1 and part 2, and let's call it calculates north beams load. It's gonna just take a grid reference, yeah, sure, and return a usize. Calc is not it's not a verb. Let's just put get. No need for a type there. And so now we can say same thing here, get north beams load for this grid, sure. And this is fine. This we can move to the bottom. Okay. I don't want to generate the grids again, so let's actually call this thing original grid, or start grid. And for part 1, let's have, well, a neutral grid that's going to be a clone of this. So we do this for part 1, great. And then part 2, we're gonna do sort of this similar thing. Start grid, clone it, spinned grids. So let's actually say grids, not by cycle, but remaining. Okay, now before renaming this, this should still count, still work. So let's run this. Okay, yeah. This is correct, right? These numbers, yeah. We have a cycle count. We have, yeah, this skip done thingy, which is kind of horrible, but it's fine. One thing that we could try is yeah, we're going to do these things. Cycle size. Like we don't need to skip if. Let's call this thing cycle detected. Okay. Yeah. And what if instead of doing like going from 0 up to this number, we say remaining cycles. Like we do it like the other way around. Say remaining cycles starts at least as this, and while remaining cycles it's not 0, we do stuff and we just decrease it. And I don't know if this is a good idea, but let's roll with it. This is gonna be like previous remaining cycles, because we are now in the hash map we are putting the remaining cycles. So this is the previous remaining cycles. So now it's gonna be previous remaining cycles minus, oops, because this is gonna be the bigger number, the current remaining cycles. That is going to be the cycle size. And I meant to do this to not have another copy of like the 1 billion here. So now what should we do? Before we did this minus the cycles that we have iterated. I think now we should just do remaining cycles here, divided the cycle size. Yeah. Oh, this is the same as doing remaining cycles minus remaining cycles mod. No, it's not that. It's not that, wait. How much do we want to skip? Or yeah, actually, no, this is just what I want to do is just mod the remaining cycles with the cycle size. Isn't this what I want? Like I'm not sure if this is exactly what I want, but let's see if we get the same. Yes, we get the same answer. So that was what I wanted, apparently, and we get the same answer for our sample. That's awesome, and I think this is much better. Like we detect the cycle size, and we mod the remaining cycle by that cycle size, and then we say, okay, cycle detector, awesome. That's great, I think. If we haven't detected the cycle, yeah, we do this thing. Okay, and then these spin grids, what is the correct name for this? Let's call it, I want to call it just like memo or something like that. Remaining cycles memo Yeah. Yeah, we try to get, yeah. Great. And we have the answer for part 2. So if you run this, it still works. I have no problem of leaving like part 1 and part 2 here on the main. Let's call this not pain, part. That was a Freudian slip. And part 2 is this, and then we print, and that's it, I think. Yeah, this looks pretty nice. Let's commit this and add a solution for day 14, part 2. Not a solution, a solution. And I think this is gonna be it. Let's, as usual, do a little let's generate a thumbnail. That will be it. So this is Advent of Code day 14. What did we do in here? We did rolling stones. I hope to not hit any copyright claim for that. I mean, Rolling Stones are a thing apart from a band, so shouldn't be a problem. I don't like the color of this that much. Let's generate another one. Oof, that is almost like too rainbowy, but I kind of like it. Day 14, Rolling Stones. And let's maybe, what is the interesting, you know what's the interesting part about this code? This horrible thing. Like all the special cases for tilt north. Yeah, I like this messy thing. So I think that's going to be the thumbnail for today's video. And yeah, this was a really nice grid-based puzzle. I sort of like doing these things where you sort of like simulate things, move things around, and you could sort of imagine, you know, the rocks moving around. I don't know, it's like a simulation thing and a sort of a tricky thing for part 2 where you have to like detect cycles on the input, but it wasn't that tricky, like at least compared to some previous puzzles. So this was a good one, and thanks for watching, and see you later. Bye bye. Bye bye.